You push your AI prototype to production, scale to 1,000 users, and the Cloud API invoice arrives. It's a number you didn't budget for. The costs compound fastest if you are using a retrieval augmented generation, or RAG pipeline. RAG is a technique that pulls relevant information from your own documents and injects it into the prompt before the AI reads it. Every document you feed into that context window, every automated tool call, and every reasoning loop gets counted by the provider. You pay a tax on every single token. But the budget is only half the problem. When you rely on an external API, you are transmitting data outside your own security perimeter. Routing proprietary customer relationship databases, financial records, or internal employee data to a third-party server triggers immediate compliance roadblocks for enterprise security teams. To protect sensitive information and cap runaway operational costs, the workload has to move off the cloud and onto your own local hardware. The open source community provides a direct solution. You can download highly capable open weights models like Meta's Llama 3 or DeepSeek and run them completely offline. But executing that locally means navigating a software ecosystem that is currently fragmented, rapidly evolving, and heavily undocumented. Developers face an immediate bottleneck, choosing between consumer-friendly desktop apps, raw C++ execution engines, or heavy enterprise serving frameworks. This comparison matrix highlights the core trade-off. Cloud APIs require zero upfront hardware, but carry high recurring costs and privacy risks. Local inference locks down your data and cost structure, but forces you to choose the exact right software to manage your hardware. If you look under the hood of popular user-friendly desktop wrappers like Ollama or Jan, you will find the same core infrastructure powering them, an open-source inference engine called Llama.cpp. Selecting the wrong local engine for your specific deployment will cause your production application to fail under load. You have to match the tool to the traffic. When a research lab releases a new open-source model, it arrives in an uncompressed format. A standard 70 billion parameter model in 16-bit floating-point precision requires over 140 gigabytes of RAM just to load into memory. That massive memory requirement exceeds the capacity of standard consumer workstations, pushing teams right back into renting expensive data center GPUs. The solution is a mathematical compression technique known as quantization. Quantization reduces the numerical precision of the model's weights, so they consume less physical space. Shrinking model weights from 16-bit to 4-bit precision drops the memory footprint by 75%. These quantized weights are packaged into a GGUF file, a standardized container for local inference. The trade-off? As file size decreases, perplexity increases, meaning a slight loss in predictive accuracy. But the operational advantage is significant. A single GGUF file contains the model weights, the tokenizer, and all the necessary metadata in one portable package. Quantization takes a workload that previously required a $10,000 server and compresses it so it runs smoothly on a standard MacBook. What makes Llama.cpp unique is its architecture. It is written entirely in plain C and C++. Unlike heavy Python frameworks that require complex virtual environments and dependency management, Llama.cpp is a compiled codebase that runs with zero external dependencies. This streamlined design allows the engine to communicate directly with the host machine, executing natively across almost any hardware profile. You can take the exact same GGUF file and run it on Apple Silicon, an NVIDIA server, an AMD graphics card, or a Raspberry Pi. The cost of this extreme portability is the developer experience. You do not get a graphical interface or automatic optimization. You have to manually configure the runtime environment via command line flags. If you have a GPU, you must explicitly calculate and assign exactly how many neural network layers to offload to the graphics card. If the engine crashes, you are responsible for tuning the CPU thread counts and adjusting the batch processing parameters until the system stabilizes. Llama.cpp strips away the guardrails. It trades plug-and-play simplicity for absolute granular control over how your specific hardware processes the model. That granular control is highly effective for a single developer. The limitations emerge when you move to a multi-user production environment. Forcing an inference engine to handle dozens of simultaneous user requests stress tests its internal architecture. Benchmarking concurrent users reveals the divide. vLLM's throughput rises steadily with load, while Llama.cpp's remains entirely flat. Why? vLLM uses parallel continuous batching. Llama.cpp uses sequential queuing, causing an exponential spike in time to first token as requests wait in a single file line. In contrast, vLLM maintains near instantaneous responsiveness, seamlessly handling thousands of simultaneous user requests without creating a traffic jam. Llama.cpp is highly optimized for single user speed, but if you expose it to enterprise-scale concurrent traffic, the queue will overwhelm your hardware. Succeeding with local AI means you have to deploy the specific engine that matches your traffic and hardware profile. This decision tree maps out the 3 dominant paths. The critical first question is whether you are building a multi-user production application. If you are an enterprise architect requiring high throughput and stable latency for thousands of parallel requests, you follow the path to vLLM. This requires heavy data center GPUs, and you will need internal engineering expertise in complex tensor parallelism to keep the server running. If you are building for a single user and want immediate plug-and-play simplicity on a standard consumer laptop, the tree routes you to Ollama. Ollama provides a seamless, app-like experience. The trade-off is that it abstracts away your ability to execute deep performance tuning. Finally, if you demand maximum hardware efficiency and complete control over the runtime environment, you choose raw Llama.cpp. Going this route means you are your own system administrator. You compile the code, map the hardware targets, and optimize the execution from scratch. Assess your actual user load, download the appropriate GGUF file,